Alrighty, gang, welcome back. Today is a fun day for us because today we're going to start moving into sections 4.4 and 4.5, where we'll be learning how to graph functions. Kind of in service to that, I want to look at some of the problems from section 4.3 where we could have drawn some graphs, but we didn't. And then we're going to go into 4.4, where we will learn L'Hopital's rule, which is kind of every Calc 1 student's favorite trick for limits. I don't know why, but people just love L'Hopital's rule, I guess because it gets them around having to do some algebra. Yeah, so that's it. That's the plan for today. We're going to talk about curve sketching a little bit from the perspective of section 4.3, and then we will talk about L'Hopital's rule. And after we talk about L'Hopital's rule, we'll be ready to move into section 4.5. Now, I want to warn you, that means we're getting really close to the second test. So let me pull up our syllabus. We can look at this together. The last section that is on exam 2 is 4.5. I'm sorry, no, 4.7, applied optimization. So we are getting there. We're getting very close. Today, we're going to talk about L'Hopital's rule. Friday, we're going to talk about curve sketching. And then we will be ready to move into applied optimization and start getting ready for the test. Now, the curve sketching section, kind of depending on how much work we need to spend on L'Hopital's rule, we may get through this on Friday. We may need to split it between Friday and Monday. That's okay. And then that will leave us Wednesday of next week for the applied optimization. Perhaps a little bit more on Friday, but then we'll be getting ready for the test. So your test is most likely going to be Monday after next. So that is, I think, November 1st. We're either looking at like next Friday. That would be cutting it a little bit tight. I'd like to give you some time to work on the study guide. So Monday after next, November 1st, is most likely going to be your second test. Let's get this in writing. So this is MAC2311, section OH1, which means it is Calc 1 honors. The date today is the 20th of October, 2021. And today we're gonna kind of wrap up 4.3, which is the section we've kind of been talking about for a little bit now, how derivatives affect the shape of the graph. We're going to cover section 4.4, which is on this rule called L'Hopital's rule. And we may introduce 4.5. So actually the little wrap up that we're doing from 4.3 is kind of the large portion of the material in 4.5. 4.5 is kind of where you put together 4.3 and 4.4. So specifically here, I'm gonna look at some graphing problems. From 4.3. And then the little announcement there. Exam 2 will be Monday, 11/1. Okay. So Yiping made some comments the other day about drawing the graph of a function after we find where the function is increasing and decreasing, concave up, concave down, mins, maxes, and inflection points. That's the bulk of the material that you would want to draw the graph of a function. So let me just grab a few problems from there. Most of this is going to be stuff that we've seen before. Let me first see if we can grab one or two of these guys and work them. And then we will get a problem where I just give you a function and we sketch the graph. me do 25 first. I don't know, 24 you don't have, you wouldn't have an answer for in the book. So for an example, this is section 4.3, number 24. I'm going to write it down and then we'll switch back to the document camera. I'm going to sketch a graph of a function f of x satisfying the following conditions. F prime of x is less than 0, and f double primed of x is less than 0 for all x. And then in part B, f prime is positive.
I'm only seeing the book.
Yep, give me just 1 second, still writing things down. F double
Okay.
positive for all x. All right, so we're going to sketch two curves here. The first curve is going to have the first derivative negative and the second derivative negative for all x. And the second curve is going to have the first derivative positive and the second curve positive for all x. Of course, there's many correct answers to this question, right? These two facts do not like narrow down a single function. There's many, many functions that could work here. So for part A, what I would recommend doing for any problem like this is you want to try to come up with the shape of the graph, right? So f primed, your f prime number line here is, there are no critical numbers. The thing is always negative, which means we're always decreasing. And the f double primed number line, also always negative. So we are always concave down. So the shape over the whole real line is decreasing and concave down. So what does that look like? Well, decreasing means we're going downhill, and concave down means that the tangent lines are decreasing in their slope. So the shape is always like this. So for part A, a graph I could draw, function that is always decreasing and concave down. What would be a, just something like this, right? Always decreasing, always concave down. Not terribly exciting. Do I have a particular function in mind here? No. Just drawing a graph that has the appropriate shape. That's it. Are there particular functions that do this? Yeah, the natural log of negative x is like this, but it has a vertical asymptote, which I'm trying to avoid. There are exponential functions that look like this, like negative e to the x or negative e to the x plus 1. Oh, wait, negative e to the, no, sorry. Yeah, negative e to the x. So this could be something like a flipped over exponential that's been shifted up. But the point here is just to go, okay, we're always decreasing because f primed is always negative. We're always concave down because f double primed is always negative, which means the shape of the graph is always this decreasing concave down shape. And then just draw anything that is like that. Starting easy. Part B is also not hard. Here, both f prime and f double prime are supposed to always be positive. Let's write that back down. So you draw your number line for f primed. F primed is always positive. So we're always increasing. F double primed is also supposed to be always positive, which means we're always concave up. So the shape of f, it's always increasing and concave up. So that means we're looking at something like this. All right, and this could just be like an exponential, just like your regular growing exponential curve. This would be an example of a function whose first and second derivatives are always positive. And here it is pretty easy to come up with actual literal examples like e to the x does this, right? Okay. That's the nice gentle problems. They can of course get more complicated. So let's take a look at 26. What else do we have here? It's 27 look like. Yeah, let's do one that's a little trickier. So for the next example, I'm going to grab number 27. This is 4.327, because here they've given us some more strict information. They've told us f primed of 0 is equal to f primed of 2 is equal to f primed of 4 are all 0. F primed is positive if x is negative. Or if x is between 2 and 4. F primed is negative if x is between 0 and 2 or greater than 4. And f double prime is positive if x is between 1 and 3. And f prime double prime is negative if x is less than 1 or greater than 3. Less than 1. This is a big list of facts about this function. They've given us a lot more to work with here. So this is going to be a lot more restrictive, right? There are far fewer functions that satisfy all of these things than satisfy these two things. But the approach is going to be the same. You draw a number line for f, draw a number line for f prime, use those two things to draw a number line that describes the shape of f, and then you're going to use that to sketch your graph. I'll give you guys just a minute to get everything down here. I know it's a lot to write. It's out of the way. There are problems like this in your homework, and unfortunately, the way WebAssign does it, you just have to like click the right graph, which is really not appropriate practice. So you need to practice drawing these graphs by hand. As before, I'm going to begin by drawing a number line for f primed. Give myself some space here. I do have some critical numbers now. All right, what are the critical numbers for this function?
0, 2, and 4.
Very good. The first derivative, f primed, is equal to 0 at 0, 2, and 4. So let me put those here. And then those are going to chop my number line up into some regions. In this first region, is f prime positive or negative?
Positive.
Positive, right? They told me f prime is greater than 0 if x is less than 0. So if x is less than 0, that's over here. So we're increasing and like going uphill. What about between 0 and 2?
Negative.
Negative, right? They said f prime of x is less than 0 if x is between 0 and 2. So we're going to be decreasing in here. I'll arrow down. What about between 2 and 4?
Positive.
Yep, we're back to being positive there. F prime is positive between 2 and 4. So back to going uphill. And then to the right of 4?
Negative again.
Good. Okay, so there's my number line for f primed. Same thing now for f double primed. They have,
Inflection points at 1 and 3.
yeah, very good. So they told me f double prime is positive from 1 to 3, and f double prime is negative to the left of 1 or to the right of 3. So I'll put 1 and 3 on my f double prime number line. So f double prime is positive between 1 and 3. So we're concave up in here. F double prime is negative outside of that interval. So we're concave down here and concave down here. And now that I have these two bits of information, I know where we're increasing and decreasing. I know where we're concave up and concave down. I can draw a number line for the shape of f. And on this number line needs to go every number from either of these. So 0, 1, 2, 3, and 4. And this is a little tight. We'll make it work. All right, to the left of 0, I am certainly increasing and concave down, right? 0 is like right here. So everywhere to the left of 0, I'm concave down. So this means we are increasing and concave down. And that looks like what? That looks like this, right? That's increasing and concave down. Between 0 and 1, I will be decreasing, right? We're decreasing everywhere from 0 to 2. And between 0 and 1, we're still to the left of 1, so we're still concave down. So decreasing concave down looks like this. And you see there that this is going to be a local max. As we go, that means we had to sail over a local max. All right, between 1 and 2, that means we're in here, we're going to be concave up. And between 1 and 2, that's still in this region, so we're still decreasing. So this is decreasing, but now we're concave up. So decreasing, concave up, that looks like this. So what happened here? We didn't go from decreasing to increasing, but we did go from concave down to concave up. So this is an inflection point. There's an inflection point at x equals 1. From 2 to 3, that means we're in here now. We're to the right of 2, but to the left of 4. From 2 to 3, we're going to be increasing. And between 2 and 3, we're still in this concave up region. So increasing, concave up, that looks like this. And if you imagine stitching two pieces together that look like that, that's got to be a min. And finally, between 3 and 4 here, or not finally, but between 3 and 4, we're still increasing because we're still in this region, but now we're to the right of 3. So we will be increasing, but now we're concave down. So increasing, concave down, that looks like this again. So this, where we go from concave up to concave down, has to be an inflection point. And then to the right of 4, we are decreasing concave down. Decreasing concave down looks like this, which means this is another max. So here's my number line for the shape of F. And you can see what this thing's going to do. It's going to have like a hill, then a valley, then a hill. Let's sketch the graph. Again, this still isn't enough to completely determine the function F. There are many graphs that do this. We just have to sketch one of them. So what I would do.
In this case, is it okay to literally just decide where on the y-axis this graph would be sitting?
Yeah, that's almost enough to determine the graph. You would also have to specify the y values of these mins, maxes, and inflection points. If you were to do that, and any x-intercepts, then that would completely determine the graph. But yeah, it's totally up to you. You can shift this up and down, and that won't change things. I guess
okay. And so for the ones where they give us the actual, then the ones they give us the actual equations, and we're actually able to find those points, then we're able to just be way more accurate.
Exactly.
Thank you.
Okay, I shouldn't have bothered drawing all this stuff over here because we're just, 0, 1, 2, 3, 4. Here's what I would do. I know I should have some sort of local max at 0. So let me just draw this in here. I know I have an inflection point at 1. Let me draw in a min at 2. Something like this. Inflection point at 3, and then a max at 4. It doesn't really matter. I'll draw it like this. To the left of 0, nothing fancy going on. So I'll just say he continues like this increasing concave down shape. Then from 0 to 1, I should be decreasing concave down. So at 1 here, I'll just say it's right here at 1, 0. We'll have an inflection point where we change from concave down like that to concave up like that. At 3, I need another inflection point, and maybe I'll put this one up here. So we're going to continue this concave up business until I get to here. And then I'll switch to being concave down. And then from 4 onwards, I should be decreasing and concave down. So that's like this. So this is one such graph. Here's the max that we have at 4. Here's the inflection point at 3. Here's the min we have at 2. The inflection point at 1. And the max at 0. And you can see how if I knew the y values of all these points, then I would have an actual very, very well-controlled graph. I would be able to draw a beautiful graph for just about any function if I have all this information and the actual coordinates of these points. The other stuff that's nice to have is the x-intercepts for the function itself. So in actual reality, when you go to try and sketch a curve, you'll want to make either a number line for f itself, or at least find the x-intercepts. I usually recommend making a number line for f, f prime, and f double prime, then a number line for the shape of f, then drawing the graph. So those 4.5 problems, they do tend to be quite long. It's usually only time to get through 1 or 2 in a full class session. But these are not too bad, right? Are there any questions about where the pieces of this graph are coming from, or how I got any of the information we got? Okay. I'm going to do one more from this section where we're given an actual function. We're going to try to find everything and graph the thing. So, where were they? I saw a few of them. Down here. Yeah, use the information parse A through D to sketch the graph. So A through D here is find increase, decrease, mins and maxes, intervals of concavity, and then sketch the thing. Well, let's do one that's not terribly bad, but not too easy also. How about 40? 45 seems fun. Let's do that. This is a bit of a doozy, but not anything too bad. And then we will move to talking about L'Hopital's rule. Copy this guy down, and then we'll flip back to the doccam. Use increasing, decreasing, maxes, concave, up, down, and IPs to sketch the graph of, call it C of X, that's fine. C of X equals X to the 1/3 times X plus 4. Okay. So the first thing I recommend doing is take note of the domain. The domain for this function, if this was a 1/2 power or a 1/4 power, then my domain would be 0 to infinity because I would need to make sure I'm not taking a square root or a fourth root of a negative number. But here, let's say 1/3 power, which doesn't have any domain issues. So my domain is all real numbers. But this is something you want to take note of right at the start. Also,
can X be -4?
It can, yep. -4 is not a problem. This factor would just be 0. And that's actually the next thing I'm going to do. I would like to find, I'd like to make a number line for the original function. So where is the original function equal to 0? Well, certainly at -4 and also at 0. Right? This factor, it's already in factored form. This factor is 0 when X is 0. This factor is 0 when X is -4. And that will chop my number line for the function itself up into 3 regions. And I just want to know, where's my function positive, where is it negative? So if I plug something negative, let's pick a perfect cube, like -8. Then this piece would be -2, and -8 plus 4 is also negative. That would be -4, so C of -8 is -2 times -4, which is +8. So my function is positive over here. Between -4 and 0, we could test -1. If we plug -1 in here, the cube root of -1 is -1. -1 plus 4 is +3, so C of -1 is -3. In particular, it is negative. And if you test something to the right of 0, both of these factors would be positive. Or you could say this is a multiplicity 1 factor, so you'll have to change sign as you hop over the 0. Next, we calculate C primed, and we'll make a number line for it. You've got some choices as to how you want to differentiate this. You could distribute the X to the 1/3 and then differentiate using the power rule, or you could dive right in with the product rule. I showed you a little algebra trick last time, and I think if we choose to differentiate this with the product rule, I'll be able to show you that algebra trick again. So let me use the product rule. First, I'll differentiate X to the 1/3, giving me 1/3 X to the -2/3. The X plus 4 left alone. And then I'll add to that what I get when I leave X to the 1/3 alone and differentiate X plus 4, that's just 1. And then if I factor out, if I force factor out a 1/3 x to the negative 2/3, what would be left here is x plus 4. And here we have to think a little bit. X to the 1/3 divided by x to the negative 2/3. That would be x to the 1/3 minus negative 2/3. Yeah, it's just x to the 1. And also, I'm dividing this term by 1/3. So I'll have a 3 there. So this is plus 3x. Because these powers always differ by an integer when you're using the product rule, this piece will always come out really nice. So what is this? X plus 3x is 4x. So this is 4x plus 4 divided by 3x to the 2/3. And I can factor a 4 upstairs. So that's 4 times x plus 1 over 3 times x to the 2/3. That is my first derivative. So what are the critical numbers? Where is this thing capable of changing sign? Where is this thing 0 or undefined?
It's undefined when x equals 0 for starters.
Good. Yep. So.
And it's 0 when x equals negative 3? No, negative 5.
Negative 1.
No.
Yeah. So this x plus 1 factor is
1.
0 and negative 1. So negative 1 and 0 are the critical numbers. Those are the places where the derivative can change sign. And this will be my number line for the first derivative, c primed. If I were to test something to the left of negative 1, like negative 2, this top would be negative. And the bottom, if I take negative 2, is cube root would be negative, but then I'm going to square that. If you wanted to, you could pick something that's a perfect cube. So we could look at like c primed of negative 8. The top would be negative 7 times 4 is negative 28. And the downstairs would be, let's see, what is 8 to the 2/3 power? That's the cube root of 8, which is 2, squared, which is 4, times 3, which is 12. In particular, we're negative here. And then this x plus 1 is a multiplicity 1 factor. So I will change sign as I jump over him. And the x to the 2/3, this isn't a polynomial factor, so we can't use the multiplicity trick. But we could say is I'm going to test something over here like positive 1. And if I plug positive 1 in here, the top is 8, the bottom is 3. So c prime of 1 is 8/3, which is positive. So we're going to be decreasing, increasing, increasing.
Sorry, wait, how did you do the one for the middle section again?
I used the multiplicity trick. So when you jump over a critical number that comes from an odd multiplicity factor, you will always change sign. So the critical number negative 1 came from this factor here, the x plus 1, which is a multiplicity 1 factor. The power of that factor is 1. So because it's an odd multiplicity factor, I will change sign as I jump over. You can take a look at that thing on the graphing polynomials that I posted to the modules if you want to see the details there.
Yeah, no, I looked at it. I could never tell which factor to go with when it came down to one that looked like this, as far as deciding what power was it.
I see. Yeah, so here the trick is we're trying to figure out what happens as we go over negative 1. And the negative 1 came from this factor. So then we use his power. His power is 1. That means the multiplicity there is 1, which is odd. And when you jump over a feature coming from an odd multiplicity, you will always change sign. But you could also test negative 1/2 or something if you want to.
Oh, thank you.
We'll be decreasing, then increasing, and then increasing. The second derivative, let's see, we have to choose what form of this we want to differentiate again. C double prime. I think probably what I'll do is pop out the 4/3. and then say this is d dx of x plus 1 over x to the 2/3. And you could use a quotient rule on that if you wanted. I think maybe better would be to use the product and chain rule. So I'll say this is 4/3 times d dx of x to the negative 2/3 times x plus 1. That way it's kind of similar to what we did the first time. So this is going to be 4/3, and then I'll open a big bracket. Product rule in here. X to the negative 2/3, when I differentiate that, will give me negative 2/3 x to the negative 5/3. And then I leave the x plus 1 alone. And then I add to that what I get when I leave x to the negative 2/3 alone and differentiate x plus 1. That's just 1. So here's my second derivative in all its gory detail. And what can I do? I can force factor out negative 2/3, and that will give me a negative 8/9 out front. And I'm also going to force factor out the larger negative power here. So that's x to the negative 5/3. And then what's left inside will be quite pretty. I've brought all this stuff out. So only thing that remains from the first term is x plus 1. And then x to the negative 2/3 minus negative 5/3 is negative 2/3 plus 5/3 is positive 3/3 is just x. Isn't that nice? So my second derivative is negative 8 times 2x plus 1 from the bracket, x plus 1 plus x, divided by 9 times x to the 5/3, moving him downstairs. So the second derivative is equal to 0 when x is negative 1/2, and the second derivative is undefined when x is equal to 0. So the numbers that go on the number line for my second derivative would be exactly those. Negative 1/2 and 0. So you see 0, something interesting is definitely going on at 0 for this function. At negative 1/2 here.
I have questions. You use the 4/3 multiple minus 2/3, but your right side doesn't have any constant. The plus it's not x plus 1 plus x.
Correct. This should be
have a constant.
Yeah, you're right. When I factored out this negative 2/3, I should have gotten a 3/2 here. Negative 3/2, right?
Yes.
Yeah, okay. So this is really minus 3/2 x. And that will change things. So let me. Yeah, so Yiping's exactly right. We're factoring out this negative 2/3 x to the 5/3. And that means the x power here will just become x to the 1. But when I divide by negative 2/3, the constant here will become a negative 3/2. So what we're really going to get here for our second derivative, and I apologize. X minus 3/2 x is negative 1/2 x. So this is negative 1/2 x plus 1 upstairs, and then negative 8 here, and then downstairs 9x to the 5/3. That's actually nice. I could redistribute a 2 or even a negative 2 there. So I can call this a 4 out front. And then when I multiply everything in here by -2, this will become x minus 2. And then 9x to the 5/3. That's much nicer, actually. Not 5/3. Okay, sorry about that. You're exactly right, and that's very nice of you to correct. All right. Everybody comfy with how we got to here? So Yiping's right. This should be a -3/2 x because I'm dividing by -2/3. The power was correct, but the constant in front was not. Then 1x minus 3/2 x is -1/2 x. And then because I didn't like this fraction here, I went ahead and just distributed this the 2 from the -8 here. So when you write -8 as 4 times -2, and then I distribute the -2, that will make this positive x, and that will make this -2. And that gets me this nice clean form. So my second derivative's number line should have 2 and 0 on it. All right, now we're ready to rock and roll. If I check something to the left of 0, I plug in -1, this top would definitely be negative, and the bottom here would also be negative, right? -1 to the 5/3. Well, the cube root of -1 is -1. -1 to the 5th is -1. So if we plug in -1, then the numerator here would be -12 over -9, both the top and bottom being negative. So I'll write it down here. C double prime of -1 is -3 times 4 is -12 over -9. And that's positive, right? Because both the top and the bottom are negative. Between 0 and 2, we could test 1. What's going to happen is that this factor stays negative. This factor becomes positive. So if you plug in +1, this is 1 minus 2 is -1, so the top is -4. And the downstairs would be +9. So C double primed of 1 is -4 over +9 is less than 0. So this is negative. And the 2 is coming from this multiplicity 1 factor. So I know I will change sign there based on multiplicities. Or you could test something like x equals 3 or x equals 8. So now I have all 3 number lines, one for the original function, one for the first derivative, and one for the second derivative. And I'll put these together, specifically the last 2, into a number line for the shape of the function. So I'm going to, on a new sheet of paper, I'm going to draw a big number line for the shape of the function c. And that will have all of the numbers from either of these guys. So those are -1, 0, and 2. So the shape of C. -1, 0, 2. All right. To the left of -1, my function is decreasing and concave up. So that looks like this. Between -1 and 0, my function is increasing. And we're still to the left of 0, so we're still concave up. So it looks like this. So there's a min here. To the right of 0, everywhere to the right of 0, my function is increasing. I can go ahead and fill in the other one. This is also increasing. And between 0 and 2, we are concave down. To the right of 2, we are concave up. So increasing concave down looks like this. Increasing concave up looks like this. Good. Good. So now I have the shape of my function. I'm also going to come back and look at this original number line just for the sign of C itself, because these will give me my x-intercepts, which I can plot. Let's also note what's going on here. This is an inflection point. And this guy, let's see, concave down to concave up, it's also an inflection point. Yeah. So I have 2 inflection points and a local min. I'd like to know the x and the y values at each of these so I can use them as points I'm going to plot. So the min is the point -1, comma, c of -1. C of -1 is -1 to the 1/3 times -1 plus 4. -1 to the 1/3, that's the cube root of -1, that's -1. So this is -1 times 3, which is -3. So that min is the point -1, comma, -3. The 2 inflection points, I'd like to find the y value at 0. That's 0, I already know that. C of 0 is 0. So that first inflection point is at 0, comma, 0. And the other one, C of 2, this is a nasty number. It's 2 to the 1/3 times 2 plus 4, which is the cube root of 2 times 6, or 6 cube roots of 2. So this other point is 2, comma, 6 cube root 2. What else is going on? I've got an x-intercept at -4, and this IP at 0, 0 is also an x-intercept. So now we're ready to draw the graph, right? One of the other things I'll say here, I've got x-intercepts, 0, comma, 0, and -4, 0. So here we go. Well, it's -1, -2, -3, -4. I know I've got an x-intercept there. So that's a point that's on this graph. Got an x-intercept at 0, 0. That's also an inflection point. We'll deal with that in a minute. I have a min at -1, and that min is -1, comma, -3. So here's that min. I'm drawing my local min behavior there. At -4, my function goes from being positive to negative. So I'm going to cross the x-axis something like this. And what else is going on? I've got those 2 inflection points. So at 0, we go from being concave up to concave down. We're also crossing the x-axis, something like that. And then over here at 1, 2, we've got the inflection point 2, comma, 6 root 2, or 6 cube root of 2. The cube root of 2, I don't know off the top of my head, right? I know it's a little bigger than 1, definitely smaller than 2. So this number is going to be a little bigger than 6. I'll say it's right here, 6 times the cube root of 2. There's my other inflection point. What else is worth noting here?
I got approximately 7.56 for that one. I just plugged it into a calculator.
That sounds good. The other thing I would note here is that your first derivative at 0 this thing, whoop, here we go. This thing actually blows up to infinity at 0. You have, it's not just an inflection point. I shouldn't have drawn it like that. It's also a vertical tangent line. So let's go ahead and sketch this. That means we're looking at something like this. When we come in here, we have a vertical tangent line. So we are decreasing concave up, increasing concave up. Now I should be increasing concave down from here to here. And then I switch to being increasing concave up thereafter. So here is a good graph of this function. Something like that. Pretty cool, right? So this guy in here is an inflection point and a vertical tangent line. This point right here is a min. This guy is an inflection point. And that would be a nice solid graph. I'm a little nervous, but let's take a look and see what Desmos says. So we're graphing X. Wow, we did good. We did good. All right. What I'm not seeing is the second inflection point at 2. Do we actually have an inflection? It's very hard to see here. I think you do go from being concave down to concave up here, but it's so faint. It's so hard to see the curvature that it really doesn't stand out. So our inflection point here looks like we're seriously concave down and seriously concave up. But the truth is this is much closer to a straight line.
How did you know there has a vertical tangent line?
Good question. So vertical tangent lines, if you think way back to when we're just learning our derivative rules, vertical tangent lines are places where the first derivative blows up to infinity. So those critical numbers, those places where your derivative is equal to 0 or undefined, those are either going to be horizontal tangent lines or vertical tangent lines. And because I know, so because C primed of X goes to infinity as X goes to 0, there is a vertical tangent at X equals 0. So that information comes from the first derivative. It's not just that this first derivative is undefined. All right, it's that that first derivative actually blows up at 0. This function, if you were to graph it on its own, would have a vertical asymptote at 0 because the bottom is 0 there. So vertical tangents are places where the first derivative blows up to infinity. You can also imagine it's kind of hard to stitch two pieces that look like this together without having a vertical tangent, right? If I'm going to connect something that looks like this to something that looks like this, it's at least possible that there's a vertical tangent there. So this should be a little hint, and then we can come back and look at our first derivative and verify, oh yeah, the bottom goes to 0 at 0. So the whole thing is going to be huge at 0. So that means we do have a vertical tangent there. And that gives us this graph, which is actually very good. All right. So let's see, how are we doing? 11:54. We're not going to have time to get through all of section 4.4, but I am going to go ahead and move on to that now. This is good. 4.4 is actually a long section, despite it being somewhat sneaky and cheeky. There are some subtleties in 4.4. So let me convey to you the basics of 4.4, L'Hopital's rule, and then we'll go into the gnarliest bits of it later. Okay. So it turns out that the language of algebra isn't really sufficient to describe all of the symbols or combinations of symbols you can write down algebraically. In other words, there are some algebraic combinations of real numbers that are not themselves real numbers. The classic example is 0 over 0. So an indeterminate form is what it sounds like. It's an expression whose value cannot be determined just from the expression. Right? So if I give you 4 over 3, that's not an indeterminate form. You know what that is. It's 4 1/3 or 4.33, sorry, 1 1/3 or 1.33333. But if I give you 0 over 0, this is an indeterminate form. You cannot tell me what 0 over 0 is equal to. It's undefined. It doesn't have a prescribed value. The value of the expression 0 over 0 cannot be determined from the expression itself. Other examples include infinity over infinity, 0 times infinity, infinity minus infinity, and then my favorites, 1 to the infinity, and I feel like I'm forgetting one here. What is our? Yeah, we'll get there. We'll get there. Where's our list? 0 to the 0, that's right, and infinity to the 0. All right, these are your indeterminate forms. The first two are called indeterminate ratios, and these are the things we can use L'Hopital's rule on. Indeterminate ratio is, the name explains what it is. It's an indeterminate form that is a fraction, right? The word ratio just means fraction. So it's a fraction where you cannot discern the value just by looking at it. 0 times infinity is called an indeterminate product. Again, because it is a product, it's two things multiplied, and we cannot tell what the value is. 0 times infinity is neither 0 nor infinity. It could be either of those, but it could also be 10. It could also be pi. It could also be 5 or -2. Infinity minus infinity. This is called an indeterminate difference. And these last three are called indeterminate powers. All right. Now, as you may guess, these show up in limits. All right. All of these expressions can show up in limits. You've seen 0 over 0 a bunch of times, right? Every time we tried to take a derivative using the limit definition of the derivative, if you just straight up plug in 0 for h, you got 0 over 0. And we had to do a bunch of algebra to figure out those limits. I couldn't have told you about L'Hopital's rule back then because L'Hopital's rule involves taking derivatives. So the logic would have been circular. We don't want circular logic. We want to know where shit comes from. All of the other indeterminate forms, I like that, yeah. All of the other indeterminate forms are managed by turning them into one of these. to turn an indeterminate power into an indeterminate ratio, you take a logarithm, and that will turn one of these into something like this. And then to turn something like this into something like this, you shove one of them downstairs as its reciprocal. Like you shove the infinity downstairs, 1 over infinity is 0. So that would be 0 over 0. Let me describe to you L'Hopital's rule. So this is a theorem. And its name is L'Hopital's rule. L'Hopital was a guy. And something de L'Hopital, right? It's like the old style French names. He was a dude, he was a mathematician, although he was not especially talented. And so one of the Bernoulli brothers, Johann Bernoulli, discovered this theorem I'm about to share with you. And L'Hopital was like, damn, that's cool. Can I buy that from you? Because he was rich. Bernoulli was not especially rich, and he was not especially prideful. So he said, sure. And L'Hopital gave him a shitload of money. And then L'Hopital went off to pretend like he came up with this shit on his own. So it's kind of a funny story of theft, like intellectual property theft. In any case, we remember it as being L'Hopital's rule. What this says is if, I'll write it like this. If lim x to c f of x over g of x looks like 0 over 0 or infinity over infinity when you plug in x equals c, then, because these are indeterminate, we're not happy with that, then you can take that limit, lim x to c, f of x over g of x, and try again, not with those same functions, but with each one replaced by their derivatives individually. So you differentiate the top and you differentiate the bottom. And if you're lucky, when you then plug in the number c, you will no longer get an indeterminate form. If you do, then you just keep going. You just keep applying L'Hopital's rule. But this is it. This is the theorem. Sorry for that pen strike. That was meant to be a period. C here could also be infinity, right? You could be taking the limit as x goes to infinity. This works great no matter where your limit is. If you've got a limit of a fraction and it looks like 0 over 0 or infinity over infinity, if you get any indeterminate ratio, then you can take the derivative of the top, take the derivative of the bottom, and try again. Well, let me show you just 1 or 2 simple examples before I have to let you go. You guys remember that sine x over x limit from way back at the start of the course when we needed it to figure out the derivative of sine, and it was like this nasty geometric proof. We had 3 triangles, or like 2 triangles in a sector of a circle, and we used the squeeze theorem. Yes, that's it. The sine x over x limit that gave us 1. Well, now we can calculate that using L'Hopital's rule. So it's true that this came out to 1. And we could now see that using L'Hopital's rule. If I plug in 0, I get the sine of 0 over 0, which is 0 over 0, which is an indeterminate ratio. So instead of grinding away with something else, like the geometry, or memorizing the limit, we could now use L'Hopital's rule. And this is the notation I like. When you're going to say that one limit is equal to another limit by L'Hopital's rule, you make some mark on the page somewhere that tells me that the reason they're equal is because of L'Hopital's rule. So here I like to say, by L'Hopital's rule is equal to, just put a little LH over the equals, lim x to 0, the derivative of sine, which is cos x, over the derivative of x, which is 1. And you see why I couldn't use this back then, the whole reason we needed this was to come up with the derivative of sine. So I wouldn't have been able to say at that stage that the derivative of sine was cosine, but now we can, which means now this limit is easy as hell. If you plug in 0 now, you get cos 0 over 1, which is 1 over 1, which is 1, as found previously by geometry, by difficult geometry. So this was a hard limit once, it is no longer a hard limit. But there's more. But wait, there's more. There's lots of other stuff that previously would have been not just difficult, but impossible that we can now manage. The other classic example, I have a clean paper. The other classic example is an exponential and polynomial ratio. So if we try to evaluate the limit as x goes to infinity of something like x cubed over e to the x, if I just plug in infinity, both the top and the bottom are going to infinity, right? This is infinity cubed over e to the infinity, both of which are infinity. You cube a big ass number, you get a big ass number. You raise e to a big ass positive number, you get a big ass positive number. This is again an indeterminate ratio. So I can use L'Hopital's rule. According to L'Hopital's rule, this is the same as the limit as x goes to infinity of the derivative of the top, 3x squared, divided by the derivative of the bottom, e to the x. Now here we're encountering that thing that I mentioned where after running L'Hopital's rule, you still get an indeterminate form. 3x squared is still going to go to infinity. E to the x is still going to go to infinity. So I'd use L'Hopital's rule again and get lim x to infinity. If I differentiate 3x squared, I get 6x. The denominator stays e to the x, and this is still infinity over infinity. So I run L'Hopital's rule one more again. And this time, the derivative of 6x is just 6. The derivative of e to the x is still e to the x. So now this would be 6 over infinity, which is 0. And kind of a neat fact here, a generalization, is that the limit as x goes to infinity of x to the n over e to the x will always be 0 for any positive integer n. And the proof, you would just run L'Hopital's rule n times. Kind of the way to think about L'Hopital's rule is as a race to infinity. Both the top and the bottom are going to infinity. But what the fraction comes out to depends on how fast the top goes to infinity compared to how fast the bottom goes to infinity. E to the x grows much faster than any power function. So if you divide any power function by e to the x and then send x to infinity, you will get 0. If the power of x is quite large, it may win at first because e to the x doesn't start off growing very quickly. But as x gets larger and larger and larger, e to the x grows faster and faster and faster. There are many other examples like this. How am I doing for time? We're at 12:10, so let me grab one more. There are some one-sided limits that are nice to look at with these. And yeah, super exponentials, we'll mess with that stuff later. For today, I just want to give you a little bit of practice. Just the logarithm thing. That's not here. Damn, that's disappointing. All right, let me do this then. So this works for some limits that might not jump out at you right away. Like the limit as x goes to 0 from the right. It did, but not the sort that I wanted. So what do each of these guys do as x goes to 0 from the right? X on its own goes to 0. What does the natural log of x do as x goes to 0 from the right?
Well, if it hits 0, it becomes undefined.
I heard it there. It's true that the natural log of 0 is undefined because we have this vertical asymptote. So as x goes to 0 from the right, the natural log of x, like Yuping says, goes to negative infinity. So at a glance, this looks like 0 times negative infinity. And that is an indeterminate form, right? 0 times infinity, but it's not an indeterminate ratio. This is an indeterminate product. So in order to use L'Hopital's rule, I first need to rewrite this so that I get an indeterminate ratio out. And that's the first kind of stumbling block in this section. L'Hopital's rule doesn't apply to indeterminate products, differences, or powers. It only applies to indeterminate ratios. So in other words, I need to rewrite this as a fraction in such a way that either the top and bottom both go to 0 or the top and bottom both go to infinity. Here's what I would do. The general trick, you're going to shove one of those guys downstairs. And I encourage you to think about the derivative you will take in the next step when you choose which one to shove downstairs. I could write this as x divided by 1 over ln x. Or I could write this as ln x divided by 1 over x. I know what I would rather differentiate. I would rather differentiate 1 over x than 1 over ln x, because that involves less chain rule stuff. So I'll send the x downstairs as his reciprocal. Now, as I send x to 0 from the right, the top is still going to negative infinity. The bottom, 1 over x, as x goes to 0 from the right, 1 over x is going to positive infinity. So this looks like negative infinity over positive infinity, which again is not 1, right? 0 over 0, infinity over infinity, they're not 1. These are indeterminate ratios. But now that it is a ratio, I can apply L'Hopital's rule. So I'll have lim x to 0 plus the derivative of ln x is 1 over x. The derivative of 1 over x is negative 1 over x squared. Right? That's x to the negative 1. So his derivative is negative 1 x to the negative 2, or negative 1 over x squared. It's true if you just blindly plug 0 back in here, you're going to get some infinity over infinity business again. But if you do a bit of algebra, just simplify this fraction. You have 1 over x times negative x squared over 1, which is lim x to 0 plus, you can cancel the x's, you just get negative x. And as x goes to 0 from the right, negative x goes to negative 0, which is 0. So x times the natural log of x goes to 0 as x goes to 0 from the right. And this is the sort of thing that will be very helpful when you go to graph a function like this, right? As is, I wouldn't know what this function does near 0. It would be hard, be very hard to figure out. And it turns out that this guy tends to 0. It's not clear at first who wins, the log, which wants to go down to -infinity, or the x, which just wants to go to 0. Here, the x wins. So the whole thing ends up going to 0. All right, this has been our quick introduction to indeterminate forms and L'Hopital's rule. We've seen one indeterminate product and a handful of indeterminate ratios. I think in your homework, I slapped you with a handful of each and maybe some of the harder ones as well. So let me take a look here. I can tell you what you should be able to get through at this point. Ugh. Come on, WebAssign, you can do it. So at this point, here we go. So yeah, this stuff, no problem. This stuff, no problem. No problem, just definitions. Where do we run into trouble? Did I give you any indeterminate powers? Maybe not. Nope, okay, you should be able to finish this homework. Yeah. I will give you more 4.4 stuff down the road, but everything in this homework right now is just indeterminate ratios and definitions. So next time I'll show you how to handle indeterminate differences, indeterminate products, and indeterminate powers. And then I may open up a second homework here.
Could you open it ahead?
Yeah, I'll go ahead and open it as soon as we finish that lecture instead of waiting until next week. Alrighty, so that's where I'm going to end it here for today, guys. Please do work on the current homework set. If you're all done with that, just watch. I'll drop the new one as soon as I can get it together for you. Remember, exam 2 is not all that far away, right? We're about 11 days away from exam 2, so make sure you're staying caught up with stuff. If you need anything extended, put in an extension request in WebAssign ASAP. I will be clearing those out between now and when my office hour starts at 1. As always, if you want to talk about stuff, come by office hour, Canvas message, Discord, you know the drill. That's it. I'll see you guys on Friday.